Dr. Chao Jiang is a computational scientist in the Fuel Modeling and Simulation Department at Idaho National Lab.
This talk is actually a joint presentation between Dr. David Anderson from Los Alamos National Laboratory and myself. I'm from Idaho National Laboratory. The title of this talk is Salt Properties from Classical and Ab-Initio Molecular Dynamics. The first part will be focused on Ab-Initio molecular dynamic studies of the aconite-containing salts. And the second part is more focused on the classical MD for obtaining the thermophysical properties that are difficult for Ab-Initio molecular dynamic simulations. So molten salt has been proposed for both coolant and fuel in the molten salt reactors, and the experimental data for the molten salt properties are sparse, and actually sometimes they are contradictory. So fortunately, with rapidly increasing computing power, we have now, so if you look at the figure below, this shows the increasing power of a single core performance with time. It's slowing down a bit, but it's still growing. And the right figure shows the number of cores per CPU is also rapidly growing. So in essence, we now have a great amount of computing power at our proposal right now. So we can use this computing power to generate a larger number of thermodynamic and thermophysical properties of molten salts with good accuracy. And finally, like the computation generated molten salt data will be used to fill the data gap and also populate the molten salt property databases, like us discussed in the previous presentation. First, I'm going to give you a quick introduction to what is Ab-Initio and what is classical molecular dynamics. So Ab-Initio molecular dynamics is based on the Schrodinger equations. Essentially, at each of the time step during the molecular dynamics simulations, the system will stop and solve the many-body Schrodinger equation to the fullest, so that we have a very accurate forces on each of the atoms. So that's why the Ab-Initio molecular dynamics is always the most accurate tool we have right now. However, it's also, there's no free lunch. So Ab-Initio MD is also very expensive. They are limited in both system size to be a few hundred atoms, and also the simulation time is limited to tenths of picoseconds. So this kind of calculation can easily take weeks or months if it's very large scale. So unfortunately, for some properties such as viscosity and the thermal conductivity that are vital to the MSR campaign. So this kind of property, they require very long time simulations, such as 1 million time steps for now, in order to get a good statistical accuracy. So I'm going to show one example to demonstrate this point. So right now, unfortunately, our computing power is still not fast enough to allow the Ab-Initio MD to tackle this kind of problems. But maybe in the future, so when we have like leaps in computing power, so we may be able to tackle this problem with Ab-Initio MD. So for now, we use a compromise. So essentially, we rely on classical MD simulations with empirical potentials, which are trained using the Ab-Initio calculated data to predict the thermal conductivity and viscosity data. This kind of classical MD calculation are many orders of magnitude faster than Ab-Initio MD. Therefore, they can get the job done in a reasonable time. This slide shows the equations we use to calculate the viscosity and thermal conductivities. So for the viscosity, we rely on the so-called equilibrium Green-Kuber method. Essentially, the viscosity can be calculated from the time integral of the stress correlation autocorrelation function shown in the integral. So, and the thermal conductivity can be calculated using the non-equilibrium MD method, which introduces a temperature gradient inside a salt by forcing some exchange of kinetic energy between neighboring atoms. And then the thermal conductivity can be calculated from the well-known Fourier's law, of heat conduction. Essentially, it's the heat flux divided by the temperature gradient. So this is an example I used to show the convergence of viscosity with MD time step. I'm used the flap salt as example. So the left figure shows the MD calculated viscosity of the salt as function of time step. You can see that the convergence will occur after about 2 million and 2 million time steps, or about 1 nanosecond. So that's why classical MD will have to be used in this scenario in order to get statistically accurate converged results. So the reason why we need such a long time is that if you look at the autocorrelation function shown in the right, it shows that the this function actually decay very slowly with time. Actually, unfortunately, it's actually even up to 40 picosecond. It still does not go to fully converge to zero. So that's why we need a super long MD time to sample this very long tail of the autocorrelation function. So that's why this kind of calculation will be very challenging for Ab-Initio MD for now. So now let's switch gears. So this part of the presentation is actually from David Anderson. So his focus is more on the actinide, like uranium chloride, in the salt. So it's more related to the fuel salt. So to begin with, the densities and heat capacities of sodium chloride and potassium chloride has been very carefully studied using Ab-Initio MD simulations. So essentially, David, he used several different methods to model the dispersion force model. And the important conclusion is that if we look at the Ab-Initio MD without any dispersion model, there's actually even the Ab-Initio MD itself has 10 to 20% error in predicting the density of these two simple salts actually. So the key conclusion is that Ab-Initio MD has to be performed together with a suitable dispersion force model, and David found that the most accurate one is the so-called density-dependent dispersion correction model, DDSC model, which, if you look at the figures on the left, is the blue circles are from DDSC calculations. They give excellent agreement with experiments. The same conclusion is also holds for the potassium chloride. So that's the method like David suggested for all the subsequent Ab-Initio studies. And also the tables below the two figures show the heat capacity of these two salts calculated using the DDSC method. You can see that the agreement with experiments are excellent for both salts. So uranium chloride is much more complicated than the two salts I shown in the previous slide. So David he found that the uranium chloride is not predicted to be insulator at all by the standard DFT. So therefore the Hubbard U method has to be used to correct this. And also the magnetic configuration was approximated by anti-ferromagnetic model. Essentially, they're kind of random in the salt. So with this kind of very advanced techniques, so David is able to calculate the density of the salt as a function of temperature. The results are actually shown in the blue dots on the left figure. You can immediately see that there are actually two sets of experimental data. One is shown as the green line, and one is shown as the purple line, I think. So you can see that immediately see that these two experimental correlations are surprisingly different, and they cannot be both correct. So there's a huge discrepancy between these two, and Ab-Initio MD actually agrees much better with one of the sets you can see on the left figure. So this is where the Ab-Initio MD can be used to judge the quality of experimental data if there exists a high discrepancy. So, and the right figure shows the energy calculated as a function of temperature. So if you feed a line through these 4 points, you calculate the slope. That slope gives you the heat capacity. And again, you can see that the Ab-Initio calculated heat capacity also agrees very nicely with the experimental data. So this is a cool example showing where the Ab-Initio MD can be used to help us judge the qualities of different experimental data when they don't agree with each other. So this slide shows another interesting application to the aluminum chloride. So aluminum chloride is a very interesting material, is that it has a very low boiling point of 180 degrees Celsius. So this kind of low boiling point actually gives us some computational challenges. So if you look at the left figure, you can see that the Ab-Initio's calculated density data actually are very far from the experimental data by a very large amount. So, and also the slope is not a constant shift. So essentially this kind of two modeling and experiments have some large discrepancy. This can be either due to the inability of the DFT method to capture the chemical bonding of the aluminum chloride, which I'm going to mention study in full maybe shortly, or due to the inaccurate experimental data. So David's suggestion is that we should look at this discrepancy more closely in the future. And also, if you look at the table, the Ab-Initio calculated heat capacity is also only very different from the experiment. So this kind of discrepancy must be addressed to help us better understand why we have such a huge discrepancy between modeling and the experiments. So now we go to the binary systems between the actinide and the salt. So here we look at both the sodium chloride and the uranium chloride system, and the potassium chloride and the uranium chloride systems. And you can see David mentioned that it's very challenging to converge the density for mixed salt solutions to very high accuracy. So therefore, there's some scattering in this kind of plots. You can see that they're not perfect, but I think they're good enough. They actually for both cases, the Ab-Initio MD and agree perfectly with the theory from one of the groups, which are shown as the purple lines. The gray lines. So if you look at however, again, the modeling can be used to help us better understand which data is better when there are discrepancy between the experimental data themselves. Now, David also calculated the mixing energies between these two for these two binary systems, which is actually this kind of data actually very important for the thermodynamic modeling of this kind of molten salt systems using the Cathode approach. So that's more for this kind of data can be used for very useful for TED, I guess. So again, if you look at the Ab-Initio results, they compare very nicely with the experimental data also cover the modeling, so which is very nice. So this shows that this kind of modeling can be very useful to provide thermodynamic data when these data are not available experimentally. And if you look at compare the sodium chloride and the potassium chloride systems, you can see that the mixing energy for the potassium chloride, uranium chloride are actually more negative than the sodium chloride and the uranium chloride systems. And also the one interesting raised by David is that the minimum of this curve actually corresponds to the eutectic composition. So it's something very interesting. So there's some connection between the thermodynamic properties and the phase diagram for this kind of very, very cool, correlation. Both the temperature dependence of the density and the energy for all the for the many salt compositions David considered in his simulations. So all these kind of plots are pretty linear. So the lower figure shows both the temperature dependent coefficient for density versus which actually they decreased a little bit with composition, and also the right figure shows the heat capacity, which shows a very nice line from all the way from sodium chloride to uranium chloride. So this kind of data can be very good data for cover modeling of these binary systems. Finally, David actually he looked very closely at the radial distribution functions of one of the binary salts, and one cool observation by David is that if you look at the peak, the first peak shows the blue. These are the interaction due to uranium and chloride. This kind of peak actually in the molten salt, the peak is actually taller than the peak shows the crosses. That's in the pure uranium chloride 3. So you can see that actually there are actually more chloride surrounding a given uranium atom than that's suggesting that even though the original base salt is uranium chloride 3, actually the local environment of uranium is actually more like in the uranium chloride 4. So this kind of thing explains the negative mixing energies. So actually David may have better explanations. So if there are questions, so please ask David. So now let's switch gear to the second part of this presentation, which is my part. So essentially, here I'm using the Ab-Initio and the classical MD simulations to obtain the thermophysical properties of the ternary sodium chloride, potassium chloride, and aluminum chloride salts. So the fundamental idea is that we use Ab-Initio calculations to do two things. First, it can be used to provide enough data to train interatomic potentials for these ternary systems. This potential will then be used in both equilibrium and non-equilibrium MD simulations to use the LAMMPS code to calculate many of the thermophysical properties, such as density, heat capacity, viscosity, and thermal conductivity. And as demonstrated in the first half of this presentation, Ab-Initio MD can be used to calculate some properties such as density and heat capacity with very high accuracy. So this will be used more as a validation of the empirical potential calculations. So first, give you some background on the what is the polarization effect. So in general, any of the ionic bond between also contains some partial covalent character due to the polarization effect, which is, if you look at the two figures below, the left figure is the perfect purely ionic bond. So on the right, you can see that the positive charge of the cation actually will attract the electrons cloud surrounding the anions actually, so that it's no longer spherical. So therefore, there are some electrons between the cations and the anions. So this gives rise to some partial covalent character. According to the famous rules of Fagen, and the degree of polarization will be more significant for cations with small sizes and also high charges. So if you compare the size of the aluminum in 3+ charge state, it's actually much smaller than the sodium and the potassium ions, and also it has triple the charge. So this kind of combination gives it very high polarization power. Essentially, aluminum chloride will have a significant covalent bonding behavior. Like as we will see shortly, this will give us some of the challenges in modeling. During the development of the interatomic potentials for this sodium chloride, potassium chloride, and aluminum chloride molten salts, I use the very low Coulomb-Buckingham empirical potentials to describe the interactions in sodium chloride and potassium chloride, which are predominantly ionic in nature. So aluminum chloride, on the other hand, has a very complex bonding behavior. So at a low temperature, it's in the solid state, it has a cubic structure, crystal structure, where each of the alumina is actually has surrounded by some chloride, and they form a 90-degree angle. If we can show in the left figure. So after they change into the gas state, actually the whole crystal will transform into the so-called diamonds, which are formed by 2 alumina and 6 chloride. They form this kind of basic unit in the gas state. And at even high temperature, the diameter will actually also dissociate into monomers. If you show in the right figure, where each alumina is surrounded by 3 chlorine, and the angle is between them is actually 120 degrees. So modeling this kind of highly complicated phase transition is actually using empirical potential is actually a very challenging task. So in this work, we have used a Stinger-Weber 3-body potential to stabilize the aluminum chloride 4 tetrahedral structure, which has been experimentally observed in this kind of mixture between sodium chloride and aluminum chloride, and also potassium chloride and aluminum chloride. So due to this kind of using a fixed angle of theta, so this model will not be able to predict the formation of these kind of monomers anymore. So this will have some consequences, as I will discuss shortly. So let's first compare the radial distribution functions for the sodium chloride and the potassium chloride mixtures. This figure shows the results from both AbInitio MD and the classical MD. So you can see that the agreement is excellent between the 2 computation methods over the 3 chemistries in this kind of mixtures. So the conclusion is that even the simple Coulomb-Buckingham potential is already adequately accurate to describe the atomic structures of the salts in the sodium chloride and the potassium chloride systems. So which is very nice. So now we go to the more complicated mixtures between the sodium chloride and the aluminum chloride systems. So the first 2 figures on the left shows the results for the sodium mixture of sodium chloride and aluminum chloride, and the right for the potassium chloride and the aluminum chloride. So if you look at the closely in the 2 figures, you can see that in the AIMD simulations, there are lots of monomers actually, like aluminum chloride 3 monomers in the liquid state. Due to the limitation of the model, the MD simulation will never favor this kind of monomer structures. Instead, it will form some of long, like a trimer structure, like aluminum 3 chlorine 10 structure. This kind of thing will form in the liquid state. In the AMD, we only see the smaller, like aluminum 2 chlorine 7 units. So this is actually due to the artifact of the potential itself. If you look at the radial distribution function below, actually the results are decent. Actually, even despite these kind of challenges, the AbInitio, the classical MD can reproduce many of the features of these results from the AbInitio MD simulations. And the same thing can be said for the mixture between potassium chloride and aluminum chloride. Again, the comparison between the AbInitio MD and the classical MD is good, but not great. So if you look at here, there's some discrepancy between the chloride radial distribution functions. So which is due to the which I believe is due to the neglect of this kind of aluminum chloride switch monomers in the molten state. So let's now we go to the results. So here the left figure shows the calculation of the densities of this kind of salts using AbInitio MD. So essentially what I did is I calculated the pressures at 5 different volumes for each of the liquid and fitted them to an equation state. extrapolating the equilibrium state to zero, actually we will give you the zero pressure. We'll give you the volume. So if you can look closely, you can see that this kind of curves actually very flat, especially close to zero. So essentially, that means the potential has to be very accurate in order to capture this kind of very slow decay tail. Actually, unfortunately, this tail will give you the equilibrium volume. So it's actually a very challenging task to actually predict even the density very accurately using the classical MD. So if you look at the right figures where I show the results from Ab-Initio MD, classical MD, and experiments, you can see that the densities from Ab-Initio MDs always agree much better with experimental measurements. And there are some, for some of the cases, the agreement is excellent. And it can also be seen that although the classical MD simulation, they did a good job of predicting the density with reasonable accuracy, they always tend to underestimate the densities for all the simulations we look at. Now let's go to the heat capacity. So here, this figure I show the Ab-Initio calculated and the classical MD calculated heat capacity for the salts in these tunnel systems. So for the sodium chloride and the potassium chloride system and their mixtures, classical MD simulation can predict heat capacity within 11% error of Ab-Initio MD results. So due to the complex bonding between aluminum and chloride, that is challenging the model by empirical potential, the error is actually somewhat larger for the system involving aluminum chloride, and the error between Ab-Initio MD and MD can be up to 19%, so which is larger than the case of sodium chloride and the potassium chloride. Now let's go to the viscosities. Unfortunately, for viscosities, due to the very long simulation time, so only the classical MD results are obtained. So, and if you look at the right figure where I plot the classical MD predicted with viscosities, which are shown as the green circles, and if we put them against the experiments, I would say the agreements are pretty reasonable for almost all the salt compositions, except one, which is the sodium aluminum chloride 4 composition. For this composition, there's some large discrepancies between MD simulation and experiments. As I mentioned before, that the formation of very long aluminum chloride chain-like complexes in the MD simulations, classical MD simulations, which are composed of corner-sharing aluminum chloride tetrahedrals. Actually, this kind of chains, they can artificially strengthen the liquid structure, therefore giving them some high viscosity. Which I believe is the origin of this kind of discrepancy between modeling and experiments. So this is the only case where the error is large. For the other chemistries, the agreement is very, very good. And finally, let's go to the thermal conductivities. So here, there only exist experiment data for pure sodium chloride and potassium chloride, which are shown in this on the left and right figures. Here you see that the MD simulation actually give excellent results in agreement with experimental data. Actually, the agreement is very good, and also I added the another literature calculating the thermal conductivity using the Green-Kuber method, which are shown as the blue triangles. Here you can see that both methods and experiments.
Hey, Chao.
Yes.
I'll give you a 2-minute warning.
Okay. Yeah, I will be very short. Yeah. Thank you. So here the agreement is excellent between the MD simulations and experiments, which are excellent. So finally, I'm showing the calculated viscosities of molten salts of each of the 3 binary systems as function of composition and temperature. You can see that the major conclusion is that adding aluminum chloride to pure sodium chloride and potassium chloride will not dramatically modify their viscosities. Actually, they even slightly decrease the viscosities. And also the viscosities of the sodium chloride and the potassium chloride mixtures are almost independent of composition. So finally, let's look at the thermal conductivity calculations as a function of both temperature and compositions. This kind of data are highly important for the MLSI campaigns because this kind of data are very expensive to obtain experimentally. So the conclusion that the thermal conductivity of sodium chloride and potassium chloride mixture will decrease with increasing potassium chloride content, and also adding aluminum chloride will significantly reduce the thermal conductivity of both sodium chloride and the potassium chloride. This is not like the viscosity situation. So now I'm going to the summary. So again, as I mentioned, the computer simulation can be used to fill the data gaps and this is very, very important, especially for salt compositions containing actinides, like and fission and corrosion products. These kind of compositions that are experimentally very difficult to explore. This is where the experiments the simulations are extremely important. And here goes to some of the summaries, which I'm not going to go over. And finally, I want to mention that there are still some challenges in modeling the complicated phase transition of aluminum chloride. So this gives us some discrepancy between the modeling and the experiments. So that's my end of my talk. Thank you.
So I have a question. Could this method also provide solubility information on actinide chloride, such as neptunium or americium chloride, in a variety of chloride salt mixtures?
You mean the solubilities, right? If I hear correctly, right?
Yes. So,
okay.
Right, yeah.
So
solubility information on actinide chlorides. So and maybe base salt mixture. I understand it didn't mean base salt mixtures like sodium or potassium, or some of the different ones you showed. So like, would there be actinide solubility in those salts? I think that's the question.
Okay.
Yeah.
So I think David's calculation of mixed energy between the actinides and the salts, actually they are important data that can be used in tests covered modeling to give this kind of solubility data. I think Ab-Initio MD will not directly tell you the solubility, but the mixing energies it provides can be used for covered modeling. That will give the solubilities. So if David can add something, that will be good.
Could you have also computed the dynamic structure factor from your AIMD simulations? So these are of interest to the nuclear data community and are distributed via the U.S. evaluated nuclear data file.
I think we haven't calculated this right now, but definitely this is something for future work, I think. Yes, that's great suggestions.
Can you speak about the uncertainty of the MD heat capacity calculations? How confident is the heat capacity prediction for UCL3?
UCL3. Maybe this is something maybe for David, I guess.
Yeah, so that's a question for David. So follow up, Jacob, follow up with David on that, David Anderson.
Yeah, but these are all from David. Yeah.
And then David has in the chat that those properties can be calculated as well. I'm not sure what he's referring to. Those properties in my comment refer to solubility. So he's referring to solubility. So that's what that was about. So all right, very good. So I think thank you, Chao. Very good.
Okay,
very impressive work.